temperature. Most generally, materials expand when they're heated and contract when they're made colder. And we're going to look at that and try to quantify it. And the thing we use, the factor we use, is called alpha, which is the coefficient of thermal expansion. And it's a number that allows us to quantify how much things are going to expand and contract. And its units are in inches per inch per degree F, or meters per meter per degree C. We are going to use degree F, not degree C. Now, we can find this value in charts and graphs, in a textbook, online. It is varies with material. Glass is one number, steel's another, different types of steel. What I can tell you is for A36 steel, the number alpha is 6.5 times 10 to the negative 6th inches per inch per degree F. A small number. You need a lot of change in temperature to get much of an action. Now we look at two different cases here, what we call the restrained case, which is unfree to move. So we draw it like this. Piece of steel is embedded in something, or the material is embedded unrestrained, so that the change in length is 0. Okay? The other case we have is what's called the unrestrained. And we draw it like this, and this signifying a roller. In this case, the stress is equal to 0. Deflection 0 when you're restrained, stress 0 unrestrained. And the formula for restrained is the stress is equal to the coefficient of thermal expansion times the change in temperature times the modulus of elasticity. The unrestrained case, we want to find the deflection or the elongation. Again, we see the coefficient of thermal expansion times the length times the change in temperature. Now, the couple of things you'll notice right away, that this equation for the restrained case does not have the length in it. It is independent of the length. So if this is 60 feet or 20 feet or 40 feet, it doesn't matter. The stress is just dependent upon the material, coefficient of thermal expansion, and the modulus of elasticity are material-related things, and the change in temperature. You'll also notice that it's not related to the area. If this is a small bar, small piece of wood, big piece, it doesn't matter. The stress doesn't matter about the area. The force matters about the area, but not the stress. Here you'll notice that the area also is not part of the equation. And you can see that pretty clearly is if I have some bar lying across the length and I lay another bar right on top of it, it's not going to expand and contract any differently just because I have 2 bars instead of 1 bar. So these are our two equations that we use for thermal expansion. And we'll see how powerful these are when we do a problem.